All right, so we're practicing our sitting. Imagine we're on a swivel chair, and I guess we're gonna have to paint you white. Okay, is that all right? And we'll be stroking you. Yeah. And we'll think. No, recording. Shh. What do you want to do? You want to get up there? You want to get up there? Get in the road? Okay, so this is the last piece we're going to talk about here, of course, right? Don't sit on the computer, right? You rebooted it last time. Yeah, you did. There's your special box. Okay, off you go. Good kitty. All right, so the last thing, it's the Fundamental Theorem of Matrixology, or linear algebra, and just putting everything together. So there's a slide or some notes you can go back to, episode 13, so that's way back here in the world, somewhere back here, right? And where we had many pieces that we put together already for the big picture. I'm just going to list them again and add what we have now, right? And then we'll finish with a picture. So we have this notion of row space being mapped to column space by A, right? So this is AX equals B problem. Everything in null space gets sent to 0. And then we had this mirror story for A transpose. Everything in left null space gets sent to 0, going back the other way. And then we understood that they have these dimensions. So this is, right, this is the rank. Right, so we've got these pieces. So we have the rank of column space and row spaces R, right? So again, it's the number of pivot columns, number of pivot variables, right? So how many rows are left after you do full row reduction. All this good stuff. And they all fit together in a very nice way. And so that's what these two pieces are. The column space and left null space divide Rm up, right? So M is the number of rows, right, in A. So they divide Rm up, right, in a natural way. So we call them orthogonal complements. So every vector in Rm can be written as a vector in left null space plus a vector in column space. We get the mirror story for row space and null space, and we realize that row space is really the column space of A transpose, so we use this notation. So that was a big thing. This is the symbol that means orthogonal complement. We can add those two subspaces together in the sense that we take one vector from each, add them together, do that every possible way. We'll get Rm and Rn. The bases, if we have bases for them, and we found different ways to get bases. Now we have the best ways to get them. We had 3 ways to get column spaces bases and 1 way to get the null space basis. So, but they combine to give an overall basis. But now we have this story, right? So row space has, and these are all the same wordings. Row space has a natural basis. It's the V1 through VR eigenvectors, right? And they come from A transpose A. They're associated with the sigma values sigma 1 through sigma r, which are the singular values, I should say. And the ones that are left over, right? There are more of them potentially. These eigenvectors, they correspond to 0 eigenvalues, and we would use them for A transpose for the null space. Same story over here, column space, but now it's the U's, and they come from A transpose. The leftover ones are a basis for left null space, and again, all of those combine for a basis for Rm. And then the transformation between these two, between row space and column space, is most easily kind of understood if, or seen if you like, with this, so A becomes sigma, right? A is now, we just sort of see it as sigma. It's a diagonal matrix. It's rectangular, it's the same shape, it's diagonal. It only has R non-zero values, and they sit on the diagonal, and they're in decreasing order. So a very powerful thing. And you know, a lot is in what the bases are doing, right? So as to whether there's rotation or flipping and so on. But once we've got those things locked down, we see that it's just we're going to take, you know, U1, v1 to u1, and we're just going to stretch by some factor sigma 1, or it could be shrinking, right? But it's just going to be a positive number. So all it can do is make it grow or shrink. So we line these two directions up with each other and see that they are, there's a one-to-one mapping between them. A very simple one-to-one mapping. This is our picture now, right? The thing that's been added are these pieces here. And right, good. And so it's the big picture. We've got row space gets sent to column space. They should be the same. They're the same dimension, right? That's what this is. D equals R. D equals R. Dimension is R. There's null space, which is really right null space. There's left null space. What happens when we do AX? We multiply X by A. Well, it can only end up in column space. So if we're trying to solve a problem AX equals B, we project B onto column space, which is to say we chop out the part that lives in left null space, and we solve this problem. We figured out that this was the normal equation story. We can't solve AX equals B. We solve instead this problem, AX star equals P. So we find an X star that can be mapped to column space and to the projected vector of B living in column space, which we call P. In principle, this is made up of two pieces. A row vector, right? So it's some linear combination of the rows of A, and then a null space vector. So any vector that A sends to 0, we can add all of those vectors, right? So if the null space is non-zero, then there are infinitely many solutions, and we add them as we need to. The new thing that we see is that there is a really great basis, not perfect, but an ideal basis for row space, for column space, for null space and left null space. And we have this very simple mapping between the basis vectors that live in row space to the basis vectors that live in column space. The sigmas are always just greater than. Let me get rid of all this. The sigmas are always they're always greater than 0, right? That's by construction. So sigma I is greater than 0, always. And they're in order as well, so that's why we can talk about approximation. But that's the big picture. That completes everything. I know, it's very exciting. The monks are actually asleep. Looks like they drank too much. But this is the completion of the big picture. But there are many things that we've many places we've traveled to get to here, and depending on what you use all of this for, different pieces will become more or less important. But singular value decomposition, many areas where there's some where there's data and there's some kind of reduction needed, SVD becomes the important piece. Anyway, so that is a big opening into linear algebra, matrixology. There are many more things you can do. If you go back to the Strang's book, we're about sort of halfway through the book, so you can look at more things there, things like discrete Fourier transform, etc., and one of the most important things we've ever figured out. Anyway, the world is discrete. Lots of things fit into matrices and vectors, and that's our world. All right, so yeah, that's a good place to stop and practice. Okay.